Okay, so I wanted to record this video as a lecture since I will be gone on Monday the 22nd. So hopefully you are watching this either in advance of that or on that day perhaps. And we're going to be picking up where we had left off, defining these integrals in multiple dimensions, but in other coordinate systems besides Cartesian. So we'd already talked about the uh, shoot, polar coordinates and cylindrical coordinates last time, and we did an example in cylindrical coordinates of an integral. So now the last one that I want to talk about is spherical coordinates. And so in spherical coordinates, our point in space, so if this is my x, y, and z axes, a single point in space is now labeled with its distance from the origin, r. This is why we specifically had defined the other kind of radius in cylindrical coordinates and in polar coordinates as a rho here, because that was specifically a radius in the xy plane, whereas this is an actual radius from the origin. So this is just the total distance from the origin, r. And then we have two angular units that help us define this. We have theta and phi. Phi is the same phi that we talked about previously. So I'm going to kind of draw in what this might have looked like in kind of cylindrical coordinates slightly to help us understand that. So this is that phi. It's the azimuthal angle, meaning in the xy plane, what is our angle from the x-axis? And then instead of defining us in terms of a distance in the xy plane, that rho, and a z-coordinate, we instead specify the rest of these units as this r, distance from the origin, and a polar angle, theta. So now we're saying we've got one angle with respect to the x-axis, which is phi, and one angle with respect to the z-axis, which is theta. And this gives us then everything we need, again, to specify any point in space with these two angles and the full spherical radius r. But then to figure out what a small volume element is in this space, we would have to allow all of these things to vary by somewhat, or by some small amount. So vary the angle here and the angle here, and we can then kind of draw a little box there. And then if I allow the spherical radius to vary as well, I get a kind of a little cube-ish shape here. Of course, it's not exactly a cube because two of these things are angular units, and so we get kind of two little arc lengths on one of these sides. But if you take that to a small enough size, you can assume that that curvature of that arc is pretty close to just a straight line, and so you get kind of a cube shape there. But we have to think about what are those arc lengths, because just like when we did this in polar or cylindrical coordinates, we're going to need to account for those lengths. Now, of course, the one in the radial direction here, that can just be called a small dr, and that one has a physical distance to it. So the dr is fine, but we will need to account for the other lengths, and let me write this out as some dr times, I'll just say a dl theta and times a dl phi, where these are the arc lengths as you vary theta or as you vary phi, those angles, and the both of these will depend somewhat on how far away we are from the origin. That much is fairly straightforward. But how they depend on that distance is not quite as simple as it was in cylindrical coordinates. So since theta varies from, in this case, 0 to pi over 2, so theta is just defined in that in that kind of 180 degree or pi radian half circle, and phi goes all the way around in 2 pi. We can think about, as you change in the polar coordinate, and then if you then change your phi angle around, you're going to be drawing different size little circles. So think about it in terms of, if I'm very close to the polar axis and I have some distance from the origin, r, and I just vary phi, rotating in the azimuth, I will draw out a circle like this. But if I, say, go to theta, meaning the polar angle of, say, 90 degrees with the same distance from the origin, and I vary phi, the azimuthal angle, I will draw, well, I didn't draw it super well there, but a larger circle as a result. Something like this. And this is with the same r, but as I varied theta, my amount of d phi changed. And you can actually think about this. What's the projected radius here of this circle? And if this is my theta, then the projected radius here would be sine theta times the actual r value, which here is on the hypotenuse of that triangle. So that means my dl phi is not just r d phi, but it's r sine theta d phi, because this r sine theta is the radius of this circle here. And then we can do the same argument again to figure out what is the dl theta. And as we draw circles, or sorry, as I vary my theta coordinate, my polar coordinate, let's see here, how do I want to say this? This arc length, as I vary theta, will just always depend on just this r, and the amount of this arc is just going to be r times d theta. So this one's a little simpler, r d theta there. And so you might want to draw some pictures out of this to kind of make sure that you're comfortable with some of these ideas in terms of how long these arc lengths are and how they depend on this. As we vary phi, the azimuthal angle, we get larger d phi, or we get larger changes when we're closer to kind of the xy plane. And so when theta is near 90 degrees, we get larger path lengths there, larger arc lengths. And this isn't the case for variations in theta. So all in all, this tells us that our volume element is r times r sine theta, so r squared sine theta, and then we'll have our dr d theta d phi. And so here then our Jacobian in spherical coordinates is r squared sine theta. And sometimes we'll see that just written as j, and here I'll just label this as for spherical is r squared sine theta, and then the full volume element was there. So to do a quick example in this coordinate system, before we go on and do our exercise that I had given out last Friday, so let's define a function, r theta phi, and this function is r squared cosine squared theta. And let's say we want to calculate the value of this over a volume defined as a spherical shell centered at the origin and ranging between the values r1 and r2. So to do that, let's integrate. This is going to be a triple integral of our function, which is r squared cosine squared theta. And I need to then multiply this by my volume element, which includes that Jacobian. So we're going to have an r squared sine theta dr, oh, sorry, dr d theta d phi. And now that I've written this out in this way, I can apply my limits. I know my r limits have to go from r1 to r2. Now, let's see if I can draw this out here to give you a rough idea. Oh, that is... Apparently I'm not as good at doing these drawings when they're not on the chalkboard. So something like this, where this would be r1 and this is r2. But otherwise we're going around the entire rest of the sphere, or in kind of maybe a astronomy or mathy term, 4 pi steradians. It's just kind of saying that the dividing out the entire kind of spherical surroundings into kind of square angular units that we use in astronomy a lot, but you might encounter in math. Yeah, so 4 pi steradians is the full angular size of the sky or the spherical surroundings. Anyway, so to do this, in the angular d thetas and d phis, the theta, we know, goes from 0 at the positive z-axis and varies down to pi, so 0 to pi in the theta direction, and in the phi direction we go 0 to 2 pi. Okay, so now we can actually think about actually integrating this, and we see that we have actually something that is, again, separable. We talked a little bit about that on Friday, but we have a function that of r, and we have functions of theta, so I can fully, and then nothing here depends on phi. So let's evaluate the phi integral first, and it will just be 2 pi out front, because all of this is constant in phi, and so I can just say that we get out a factor of 2 pi from integrating those limits. Or rather, this would be a factor of phi coming out, evaluated from 0 to 2 pi, which gives us 2 pi out front. Okay, then the rest of this is separable, so I'm going to write this out in a separable fashion and say we got 0 to pi of cosine squared theta sine theta d theta, And then that is going to be multiplied by the r integral, r1 to r2 of r to the 4th power dr. And that is what we will need to do. So here, this one's easy to do. So we have 2 pi. Let's just talk about this one now. We've got r to the 5th over 4 evaluated at those limits. So we would have, say, r2 to the 5th. Over 5. Sorry, I misspoke. So I'll put the over 5 out here. And then, there we go. r2 to the 5th power minus r1 to the 5th power is going to be in there somewhere. And then the last piece of this is we have to evaluate this one. And we could do a u substitution or something like that here and say that u equals cosine theta, and then our du would be minus sine theta d theta. And so what we would get there would just be an integral from here. We would plug in, okay, what's cosine at 0 and cosine at pi? So we'd say 1 and minus 1 are my new limits there. And I would have minus u squared du for that integral. Now, this might be a reminder for our back to our calc classes, but if I can just use this minus sign to flip the order of these limits there. And so that's what I will do. I'll say 2 pi over 5 times r2 to the 5th minus r1 to the 5th. And this is now an integral from minus 1 to 1 of u squared du, which I'll just put this all in here just so I don't have to write it again. And this integral would become u to the 3rd power over 3 evaluated from minus 1 to 1. And again, we've got that, whatever all that is. And then inside here, we're going to have 1/3 and then minus another 1/3, because we're going to get minus 1. Okay, let's see. Let's just write 1/3 there, and we'll have minus, and then this will become minus 1/3, like so. So this will actually evaluate to, I don't know why I wrote it in there. Sorry. So this is times all of this thing again, the 2 pi over 5, and then the difference of the radii to the 5th power. Okay, so then this piece here evaluates to 2/3, and so all in all, we'd get 2 times 2 is 4 pi over 5 times 3 is 15, and times then r1 to the 5th power minus r2. Nope, I got that wrong. r2 minus r1 to the 5th power, like so. And then that would be our final answer. So the main pieces here were to remember this Jacobian, applying my correct limits of integration here, and realizing that this was separable, so we could kind of put all the thetas over here and all the r's over here, and then it becomes just a bunch of relatively simple integrals that we can do. Okay, so with that, I'm going to have us take a stab at this exercise that I handed out, and should be on Moodle if you don't have your copy of that I handed out on Friday. But I'm going to work through this exercise here now. So what I would say is pause the video now and try to work on this yourself and see how far you can get on each problem. And then once you get stuck or once you finish, then play the video and either check your work or just make sure things are going well, Or if you need some help, watch until you realize what was going wrong with your work earlier, and then pause the video again and try to keep going from where you are kind of catching back on to understanding what we're doing, just so that you get that hands-on experience. And then if you run into any more issues, play the video again and keep watching my solution. Okay, so I'm going to do this. This first integral that we want to evaluate is a double integral of e to the minus x minus 2y, all of that in the exponent, dx dy, evaluated from 1 to infinity and 1 to infinity, like that. And to do this, we can just think about what this first inner integral is going to do for us right away. And when we do that, remember, we're treating all of this y stuff as though it was a constant. And so we can evaluate this almost immediately, because this is effectively e to the minus x plus some constant. So I'm going to leave this y integral part of it alone, and I'll just get minus e to the x minus 2y evaluated at those limits, 1 to infinity. And then, of course, we have our dy out here still. And then we can evaluate those limits before we go and do the y integral. So I'll leave that y integral here. And what we're going to get, if we have, oh, sorry, there's still a minus x there. We've got minus e to the minus infinity now. And so e to the minus infinity will be just 0. So we get a 0 there, and then we get, so let me say 0 minus whatever the thing is when we're evaluating this at 1, and then we'd have a minus e to the minus 1 minus 2y as the other piece of this dy. And so this minus cancels that one, and so we will end up with a positive exponential in there. So we have 1 to infinity, e to the minus 1 minus 2y dy. And then this one is just now a 1D integral that we should be able to do. Here we're going to have e to the minus 2y plus some constant here. And so we'll have a minus 1/2 e to the minus 1 minus 2y when we evaluate that, and then we have to evaluate it at these limits. And again, we can do that when we plug in this infinity here. We'll get e to the minus infinity again, and so this one, we'll still have this constant out front, and we'll have a 0. And then we have e to the minus 1 minus 2, so minus e to the minus 3, like so. And then that minus will cancel this one, and we'll get 1/2 e to the minus 3, or 1 over 2 e to the 3 as our answer. Okay, so that was that first one. It wasn't too bad, but it did show us kind of how we can do these inner integrals first and then do the outer integrals afterward. So then I want to do a slightly more complex version of something we did in class, and do an example where we have now two curves that we have to evaluate a function over the range in between the two curves. So my first curve is x equals minus y squared, and my other curve is y equals x over 2 plus 12. So first thing first is let's just try to sketch this region. So x equals minus y squared will just be something like this. It's always going to be negative, or x will always be negative, so it's never going to cross into the positive x values here. And it's just a parabola, but it's a parabola facing off in this direction, like so. And then my other equation says, well, I've got a slope of a 1/2, and I should cross the x-axis at some positive number up here. And so I could just, and it's just a line, so it's something like this. And we can then draw this in, and I'm going to shade the region that we're talking about. And for us, we're going to actually want to figure out a couple key points here and here that will help us determine these limits in these different directions. And maybe even also here. Of course, this one is just the origin, 0, 0. But it might be important because it's the furthest extent in the x direction. And then here and here define the furthest extent in the y direction. So let's find where these intersect, and we can do that just by plugging one equation into the other. And so in this case, if we say y equals, in this case, where there's an x here, I'm going to plug in minus y squared over 2 plus 12. And if I just multiply everything by 2 and put it all on one side of the equation, I'll get a nice looking quadratic. So I'm going to do that by multiplying everything by 2. 2y equals minus y squared plus 24. And then I'm going to put it all on one side. So I'll get y squared plus 2y minus 24 equals 0. And in this case, this is nicely factorable. We can say y minus 4 times y plus 6 equals 0. So my y values are going to be either 4 or y equals minus 6. And those are going to define these locations here and here. And then to finally figure out the x coordinates of those, we just need to take minus y squared. So then the x associated with this one would be minus 16, and the x associated with this one is minus 36. So that all works out, and now we know our 2 points. So I'll label them minus 16, 4, and minus 36, minus 6, like that. Those are my points of intersection. And lastly, if we have a uniform mass density, surface mass density, sigma, there, let's calculate the total mass, which will just be double integral of the sigma dx dy. This constant sigma, of course, could just come out front, but I need to figure out what my limits of integration are. And so if I do it this way, where I've written dx as the inner integral, remember that means I'm drawing these kind of horizontal stripes here that I want to be integrating. So now I have to figure out what is my lower x limit and what is my upper x limit. But they're actually just defined by these two functions. So the lower x limit will always be the one defined by this line. So I would need to just solve this equation for x. So x here would be multiply everything by 2. So we have 2y minus 24, because I have to move this 24 over to the other side to solve for x. So that's my lower limit. My upper limit is just going to be minus y squared, because we already have this one solved for x. So that's what I'll plug in here. 2y minus 24 and minus y squared. And so then my x limits are between those two functions, but my y limits are just going to be, in this case, between these two values. So I can just say between minus 6 and 4. And again, that's because we've already accounted for the variation in x as we change, or the variation in my limits in x as I change in my y coordinate doing here. So I just need to account for what's the total extent in the y direction here and here. Okay, so we're going to evaluate this. You can plug sigma out front and say minus 6 to 4, and then we don't have any x here, so I can just say this is x evaluated at these two limits. Like so. And then if we do that again, we get here, we get the integral from minus 6 to 4, and then we would have minus y squared, subtracting the lower limit, which would be 2y, and then when we subtract the minus 24, we get plus 24, and all of that is dy, like so. And we have sigma out front still. When we do an integral of this, we will get a minus y cubed over 3. We have here minus y squared, and then we have plus 24y evaluated from minus 6 to 4. And when you plug all of those numbers in, you're going to get something about 166.7 sigma. And so you can just plug in those numbers into your calculator, figure out what that evaluates to, and double check that I did that right. But then that would be the end of that problem. Okay, and then there's one more on the back of that exercise that we can still finish off and say, problem 3, find the moment of inertia of a rectangular region that starts at 0, 0 and goes to 2, 3. If it has a surface mass density that depends on x and y of x y squared. So there's literally 0 mass at the origin, but as you go further and further up, the total mass of this corner weighs a lot more than anything down near the origin. And let's say instead of going around the y-axis like we did before, now we're going to rotate around the x-axis. And so in this case, we want to be thinking about how far are we from the axis of rotation, which will now be our y coordinate that will matter. So di will be y squared dm, or y squared sigma dx dy. So some little integration element dx dy. And we have to figure out the total mass present there, which will depend on sigma. So in this case, my I, for the full integral, I want to start my double integral. It will be y squared times sigma, which is xy squared, so it'll be x y to the 4th power. And if I do dx dy, then my limits of integration in x have to go from 0 to 2, and in y from 0 to 3. And we can evaluate this, and of course we can see, since these limits of integration do not depend on x or y, and we have functions that look like so, these are, again, kind of, you could think of these as separable, or we could just think, okay, let's just handle the x first, say 0 to 3, and say this becomes x squared over 2 times y to the 4th, because that's constant in this inner integral, and evaluate that from 0 to 2, like so. After we evaluate that, we would have, of course, the lower limit gets killed off, the upper limit becomes 4 divided by 2, So then we have just a factor of 2 out front from the x portion of the integral, and then we have from 0 to 3 of y to the 4th power dy. So 2 times y to the 5th over 5 from 0 to 3. And when we plug those numbers in, we'll get 97.2 kilogram meter squared. Again, check my work. But that should be our answer, and that should not have been too hard, as long as we can remember our moment of inertia formula and how we can apply breaking that dm into something that we can actually integrate and doing this double integral. So hopefully you were able to complete that. And if you have any questions on that exercise, I will post my solution as soon as I'm back from my break. So that should be, I guess, sometime I'll post it sometime Wednesday next week. So, or this week when you're watching it. And yeah, hit me up with questions. Okay, so then moving on to finish off a little bit more before we end this lecture today. Let me make sure. I want to talk a little bit about a couple different kinds of integrals that will be useful for physics problems that we will encounter. So we've introduced the basics of the integration that we're going to be working on, and integrals in multiple dimensions. Now let's apply some physics, and let's talk about work. So if we think back to our physics 1, work was force dot product with displacement, meaning that if I take a box and I push on it with some force, and it then as a result moves by some amount, I have done work on that box. If we have, so here, let me draw those again. If the path that it takes, if this displacement isn't a constant value, or sorry, a constant, like it's not straight, or so it takes some curved path, or if the force isn't constant throughout that push, meaning that either its magnitude or its direction is changing throughout, then to calculate work correctly, we will have to do an integral of little bits of work, because the work will be changing constantly as we go around. And so we could then say that we have some force dot product with some displacement like that, some little tiny bit of displacement, and the force over that bit of displacement will be constant, assuming we take the displacement small enough. And this kind of integral is something we call a line integral. Oh gosh, how do I? Integral. There we go. And if we think about what this formula means, this dot product tells us that that we're really taking the displacement times the component of the force that's in the direction of the displacement. So if, for example, I have a block that's moving in this direction, and I push on it with a force downward, but it's sitting on a surface like this, that's going to do no work, assuming the block does not move downward as a result, because this is perpendicular. But say instead I push on the block like this, there is a component of this force that is in that direction. So if I break down that force into two components, there's a component perpendicular, there's a component perpendicular to the force, and a component perpendicular to the displacement, and a component parallel to the displacement. And only this part, the component in the same direction as the displacement will contribute anything to the work. More generally, this type of line integral we can write as some integral of some vector field, which I'll say v, dotted with some kind of displacement vector, maybe along some curve, where now let me draw out, say we've got some shape of a curve. Let's just say this might be the path that you're taking. So this is kind of the path that you take as you push the box through here. And at each point in space, this vector field is going to point in some direction. And locally, this ds is just pointing tangential to this curve. It's always pointing along the curve as you're moving along. That's what this ds is saying. Just a tiny vector pointing along the curve at any given point in space. So this, when we write a little integral sign with a little like c here, is or just any, usually a c, talking about, this is saying this is a integral along a curve. Or sometimes you might see an integral sign where we do something like this. And we have this kind of little circle in our integral sign. What that means is we're integrating along a curve, but it is a closed curve, meaning it loops back on itself and ends where it starts. This is fairly common for these type of line integrals, that you might want to do something on some sort of closed curve. And as we'll see later on when we talk about conservative forces like gravity, if you were to calculate the work done by a conservative force on a closed curve, it will end up being exactly equal to 0. But we'll talk more about that later. So I want to talk about a couple ways that we can evaluate these type of line integrals. So let's write out an example field. So these have to be vector fields when we're doing line integrals, because we have a dot product as part of our definition. So this will be something where it has a vector component. So I'm going to define this as xi hat plus y z squared k hat. And let's say we have a curve defined by z equals y squared equals x to the fourth. And you could think about what that looks like in a couple different kind of two-dimensional projections. That in the xz plane, this is a very quick z goes as x to the fourth, so it very quickly rises like so. And then in the zy plane, it'll go a little more slowly up, but it's still rising as y squared. And remember, this is two projections of the same singular path that it would take through 3D space. So if we wanted to evaluate, as we move along this curve, the value of the function f, the vector field f that points in the direction of this, we would have to figure out how can we express this ds. We could do it a couple different ways. We can say, well, ds is a vector that points a little bit, some small dx in the I hat direction, plus some small dy in the j hat direction, plus some small dz in the k hat direction. And then, of course, we know how to relate x, y, and z. So we can say y equals x squared and z equals x to the fourth, just using this equation again. This is an equation that defines the path that we're going to take. So we can rewrite our dy and our dz in terms of our dx if we wanted to. So dy is going to be 2x dx, and dz is 4x cubed dx. So there's a couple ways we can now evaluate this using this. We can say the integral on this curve of f dot ds is, well, let's write these out component-wise, because that's what a dot product can be done. So let's say we have the fx component dx plus the fy component dy, sorry, here we go, plus the fz component dz. And when I have this integral like this, where I've got something fx dx, fy dy, fz dz, I can split this integral into an integral just over x and plus an integral just over y plus an integral just over z. And so I'll do that and say this one, oh, I guess I think I forgot to define that we're going to start at the origin 0, 0, 0 and go to the point 1, 1, 1. So I need to specify the beginning and end of my path if I'm going to evaluate this path integral, this line integral. And so all of these limits are going to go from 0 to 1 in each of these dimensions. And then I can just plug in what are the components fx, fy, fz, and fx is just x. So this is integral 0 to 1 of x dx. Fy is actually 0. There's nothing here that depends on the j hat component. So then this is just 0 plus the fz, which is going to be 0 to 1 of y z squared dz. Okay, so now this one is easy to do because it only depends on x, and we've got x limits, so we can just evaluate that, and it will be 1/2 x squared evaluated from 1 to 0, which is just 1/2. We've already handled the 0 here, so then we have to figure out this one. And this is the little bit tricky because we've got a y z squared, but only in terms of integrating in the z direction. So I want to rewrite this y in terms of z, and I know how y varies with z along the path that I'm taking, and it's defined by this functional form that defines the path. And so y squared equals z, so y equals square root of z. So I can plug that in here. From 0 to 1, square root of z times z squared will give me z to the 5/2 power. And finally, in that form, it's something that we can evaluate. 1/2 plus, this becomes z to the 7/2 over 7/2. We'll evaluate it from 0 to 1, or 1/2 plus 2/7 times z to the 7/2 evaluated. Those limits, which is just going to be, again, 1. So it's 1/2 plus 2/7, or 11/14. And you can check my work on that one. But there's another way of doing this same integral, and I want to also show you that, where instead of writing it out in terms of 3 separate integrals of these components, which we can do because we've got this dot product. Well, I'm going to start the same way and say, well, I'll skip writing the limits for now. I'm going to say we've got x dx plus 0 plus y z squared dz. But what if instead of trying to evaluate over dz and dx, what if I instead wrote all of this in terms of a dx so that I could evaluate only as I varied in x? And so let's do that. So I'll skip the limits for now until I get this all in terms of x, but I get x dx, and then I have y, which y squared equals x to the fourth, so that means y is just x squared, and z squared is, well, z is equal to x to the fourth, so then that means z squared is equal to x to the 8th power. And I already sort of figured out how dz looks in terms of dx. So if I wanted to just rewrite this, I could put in a 4x cubed dx. And that's why we did all this work here, so that we could do this. And now that it's all in terms of x's, I can plug in my limits in x, which go from 0 to 1, and I get 1 integral of x plus 4x to, what, the 13th power? And then all of that is dx. I can do that integral, and that becomes, this becomes x squared over 2 evaluated at the limits, which is my 1/2. And then added to that, I'm going to get 4 times x to the 14th over 14, evaluated from 0 to 1, which will, the x will just give me 1 there. So this will be 1/2 plus 4/14, which again was the same as 1/2 plus 2/7, which will again give me 11/14, and that checks out. So, good. Both methods gave me the same solution. So that's an example of performing one of these line integrals, and we had 2 separate methods for trying to go about doing that. And these will be very useful later on, especially when we get into the vector calculus stuff in chapter 8 as well. So we'll keep seeing these, and we'll get more experience with these. The other important kind of integrals that I want to talk about right now, that we'll spend a lot more time on Wednesday going over, is surface integrals. So this is going to be a 2-dimensional integral, but it will be a 2D integral of a vector field and how much of that vector field goes through a surface. So I want to start with an analogy of kind of like fluid flow through a pipe. So I'm going to say, here's the velocity of some fluid in this pipe. And let's say I then have some surface. Let's just call it like a hoop. Like a hula hoop that water is going to flow through inside this. And depending on how I orient this hula hoop, I might get more or less water in this pipe flowing through it. If I have a hula hoop of a fixed total area A, if I tilt it more and more like this, perpendicular to the flow of water, I'm going to get less total amount of water passing through it. Whereas if it's exactly how do I say this? If it's exactly perpendicular, if it's face on to the flow rather than edge on to the flow, we can draw all these lines through and see that some of the lines will start to miss the hoop, meaning some water is no longer going to flow through the hoop. And so in order to figure out how much of a vector field will flow through some surface, which is what this surface integral is really going to tell us, we kind of have to define for any given surface an orientation. And so the way I'm going to do that is I'm going to draw a vector perpendicular to the surface. So here you can see these three vectors pointing perpendicular to the surface, where the surface is kind of just the plane defined by this hoop that I'm talking about. And the amount of water going through the hoop will be maximized when the vector field and this vector I've drawn perpendicular to the hoop are aligned with each other. And if they're 90 degrees away from each other, it will eventually go to exactly 0 if no portion of the face of the hoop will allow any water through it. So then I'm going to define a thing that I'm going to call the flux, which is basically how much water is moving through the hoop. And I'm going to say it's that vector field, or in this case the velocity of water. It's actually a dot product with that area vector. So I define the area, and now I'm defining the vector, the area vector, as this vector that's perpendicular to the surface, and the magnitude of this vector will be proportional to the total area. So if you have more area, the magnitude will get bigger, but the direction is always perpendicular to the surface. And so then we can use our definition of a dot product to tell us that this is the magnitude of V times the magnitude of A times the cosine of the angle between them. And you can kind of think of this in two different ways. Either you can think of grouping this cosine with this magnitude of V and say this is V cosine theta times A, which tells you this is the component of the vector field, or the component of the velocity that is in the direction perpendicular to the surface, or normal to the surface. So you could define this vector field which points in this direction, and if, let's say my surface is tilted like so I have a vector pointing that way, I could define, well, how much of this vector points in that direction versus perpendicular to that direction. And this is the component we're describing, V perp, when I write it out this way. So how much of the vector field is pointing in the direction perpendicular to the surface? That's one way of thinking about it. The other way of thinking about it is, let's group together the terms like this. So then I have V times A cosine theta. And if we think about it this way, then what I'm really saying is, well, let's project, now let me redraw this again. Here's my vector field V, and here's my tilted A. Well, let's project that this way, and see I'm getting a smaller amount of area now than the total area, but this is the projected cross-sectional area that the vector field V would kind of see. That here, now I can actually kind of show you here. So here I have a ring with my fingers or hand that is perpendicular to the camera, but if I just tilt this, the amount of area you're seeing through is smaller, even though the total area of this little circle is not changing as I tilt it with respect to the camera view, the cross-sectional area that you see is smaller. That's the same idea here, that when we tilt this more and more, the amount of area seen by this vector field v decreases. So that's going to be important because it will describe how much of this vector field is allowed to pass through a surface. And now if I have, say, some weird three-dimensional, so imagine that this is some 3D, I guess I drew almost like a weird peanut shape here. So this is a 3D surface that's closed, meaning you could kind of pick up this object and there's no holes in it. And if I have some vector field passing through this, maybe going in and then coming out the other side, or going around it in some way, I could try to figure out what's the flux of this vector field through this surface. And that's going to be useful a lot of times, and in particular with, say, something like an electric field, which is going to be the example we'll talk about at length on Wednesday. So this thing here is called a closed surface. And we need to define what we mean by something passing in or out of this, and what that means for the flux. So something that is coming from the inside of the surface and going outward, we will call that positive flux. This is just a convention, but it's a convention that's commonly used, is pointing outward from a closed surface. Now note that that doesn't work if the surface isn't closed, because then there's not a clear inside or outside, but if there is a closed surface, we can use this convention, and a negative flux will be the opposite, pointing in to a closed surface. So it's entering into. So the way I drew this here, we have some amount of things going in, and then the same amount of things going out. So that's actually another important idea, that we can have maybe zero net flux, because if everything that goes in eventually goes out of that surface, then that would kind of sum up to be zero. And let's see here. So our surface integrals, and so sometimes we'll define flux as like a capital phi, and that will be this surface integral, a 2D integral of the vector field f dotted with some area vector dA. And if this happens to be a closed surface, we would draw one of these again. So just kind of like we did with the closed loops in line integrals, we could have a closed surface integral as well. And to do this right, there's a couple ways of breaking down dA, and we can either define that in terms of maybe parametrically, in terms of some other coordinates, because now remember, even though this shape might take up 3 dimensions, it is a 2D surface, so we can kind of project it into 2 dimensions that way, by writing out some parametric equation, or there's other ways of kind of writing this out if we can define the surface as a function of just, say, maybe x and y coordinates. Now that won't always be possible, but sometimes it will be. So I want to do just an example of each of those. if possible. I know this is going a little bit long, but I want to get through some of this before Wednesday. So let's do an example where we define this parametrically. So if I have a surface that I can define as everywhere on the surface falls, could be defined in terms of these values u and v, which the x, y, and z coordinates of some vector that is on the surface of this, or sorry, that, here, let me draw something like, I've got some weird bean-shaped surface in these 3 dimensions, whatever, and I can draw a vector from the origin pointing to a spot that exists on this surface, and the x and y and z coordinates of that vector can be written out in this way. This is what I mean by parametrically. So the x and y and z components are all themselves functions of just 2 variables, u and v. So my example here will be v cosine. U is my x coordinate, v sine u is my y coordinate, and z is v squared. And actually, let me see, I have this somewhere. Let me find it again. I had a plot of this I wanted to show. Not sure if I'm going to find it quickly. 1 second. Okay, I think I found it here. If I go, there we go. So here is that shape, and you can see I define my u and v. Here u varies from 0 to 2 pi, and v goes from 0 to 3. And I create a grid of those u and v points, and I define x, y, and z as v cosine u, v sine u, v squared, and I can then create a surface plot. And so you can kind of see this thing is this kind of parabola type shape, but in now 3 dimensions. Okay, so I'm going to quickly go back to my camera, and let's continue where we were. So how do we find dA? So in order to find that dA, we need to figure out how, if we let u and v vary, how will x, y, and z vary as a result. So to do that, we can think about, we're at some point in space, x, y, z, and here's my radius vector that depends on those coordinates, and as I vary u and v just a little bit, I will create a little bit of surface area like this, which will take me from my x, y, and z coordinates that depend on u and v to, so this, here, let me write out the components here of this, which would be x of u, v, y of u, v, and z of u, v. And when I vary those, I get to some other point, which is x of u plus du, and v plus dv, and y, which has u plus du, and v plus dv, and z, the same thing, u plus du, v plus dv. I've changed v and u by some tiny amount, and I've traced out a little bit of area. And if I zoom way in on what I just did, so here's that original point, and I can draw out this little patch of area and think about the path that I took to get there. This here is as I vary the value of v, I move in this direction. And you can think about this as being a partial derivative of r as I vary the value of v times the amount by which I've changed the value of v dv. And then this side of this little kind of square or shape here will be as I vary the parameter u, I move in this direction, and then I move in that direction by an amount equal to the partial derivative of r with respect to u times du. And so that gives me some amount of dr that I've changed. And then as I vary both of them, I end up getting to some other point in space like this. So dr du times du is a small step in a direction here as I increase u at constant v, and is tangent to the surface that I'm actually defining. And the same is true as I change v. So dr dv times dv will also be tangent to the surface. So I want something that's perpendicular to the surface to find my dA vector. So I'm going to take dA in a vector sense as the cross product between these two vectors. So dr du du, now this is a vector, crossed with dr dv dv. So this one's du, that's dv. And then these things are just some scalar quantities. So really I'm taking dr du, which is a vector, and crossing it with dr dv, which is a vector. This product will be a vector, and I have a du dv out here to give me some integration element. Okay, so that is a lot, and you can define it, but it is a challenge to do. The other way, which is a slightly easier way, would be to define the surface as some function of our other two coordinates. So here we could do this by saying z is x squared plus y squared. Again, I'm going to swap over to show us doing that. It's going to be basically the same surface, but now instead of defining it in terms of u and v and getting kind of this nice circular shape, I have to have limits in x and y, and so I get kind of these extensions into the corners that we didn't have before. But I can otherwise define this exact same shape, just in a different way. So we can get that same shape. Here I'm going to go back to my camera, and if we do that, let's look at maybe a cross section of what that should look like. A ZX cross section. And I want to get a dA vector here. And to do that, and have it be perpendicular to the surface, we're going to need to figure out something related to how z changes as a function of x and how z changes as a function of y. And the component in the x direction here will depend on how z changes in the y direction, and the component in the y direction, if we drew another cross section of z with y, the component in the y direction of this vector will depend on the j hat and how what the slope is of z as a function of y. And so the book goes into great detail with this, but I will just kind of define this. We have the partial z, partial x, I hat, minus partial z, partial y, j hat, and then we just have plus k hat. And all of that gets multiplied by some dx dy size to give us an integration element. Okay, so that's a lot to break down these surfaces. It is a challenge. I wanted to do kind of one quick example here before we end today. And I know this has gone long, but let's do this one parametrically with that same surface we were talking about, with r equals v cosine u I hat plus v sine u j hat plus v squared k hat. And my dr du, which we need to calculate, remember, is just going to be taking the derivative with respect to u of this, which will be minus v sine u I hat plus v cosine u j hat. So that's my vector dr du. And dr dv, we just take the derivative, the partial derivative of this with respect to v, will be cosine u I hat plus sine u j hat plus 2v k hat. Here we need to do a cross product. So we have to think back to when we may have hopefully seen our cross products before sometime in the past. If we have not seen them, I will have to spend some more time talking through this at sometime soon. But I'm going to do this now, assuming we have seen at least a little bit of this. The way I always like to do this is kind of write it out in this fashion where it's a 3D determinant. You don't need to have learned exactly what a determinant is yet. We will talk more about that later in the semester. But you put the I hat, j hat, k hat unit vectors up here. Then we put the components of the first vector in the second row. So the first one will be minus v sine u. I should have given myself some more space to write this all out. So let me do that. So then the second component here is v cosine u, and then 0, and then cosine u sine u 2v. And to evaluate this, I'm going to have to spend some more time talking this over to do determinants right and to do cross products. But for now, to get the I hat component, we cross out the first row and first column. We do cross multiplication here. We do this times this, subtract this times this. So we'll get 2v squared cosine u, and that's our I hat component. To do the j hat component, we cross out the top row and this column, and we do this times this, subtract this times this, except with the j hat component, it comes along with an extra minus sign. So we'll have 2v squared sine u j hat. So that's plus that. And then lastly, the k hat component like this, we'll have minus v sine squared minus the other component, which is v cosine squared u, keep forgetting that. Wait, sorry. Sure, I'm kidding. That's k hat there. And this one we can see is just going to be, we've got sine u and sine squared and cosine squared. So this will just be 2v squared cosine u I hat plus 2v squared sine u j hat, and then just minus v k hat, because this will just add to 1. Okay, so sorry for glossing over a bit of this. Might need to review a cross product a little bit more later on in the semester. For now, I will leave it as this, and if you need to perform one of these, might just need to review a cross product, but it again yeah, I'll spend some more time with this when we get back, going into a little bit more detail there for anyone who needs a reminder on cross products. But to actually finish off a problem like this, we would need to have a vector field, because we know that to get a flux we need not only the area here. So we've just basically defined our area vector. This would be our dA would be this, du dv, but we also need our vector field f. So let's define a vector field f as, say, v squared plus 3, and I'll just say that this vector field only points in the k hat direction. So this only has a z component at all. So here, when we do this dot product, if we do, double integral of f dot dA, conveniently enough, we're going to not have anything from the I hat or j hat terms, because the vector field itself only has a k hat component, and we're doing a dot product between them. And so here we can get just we still have a 2D integral over the whole surface. Here we're integrating over u and v. And then I've got my f, which is going to be v squared plus 3, dotted with here just a minus v is the only thing that we get from the from this dA, because we're only taking the component that is of the area vector that points in the direction of the vector field A, or the vector field F. And this is just du dv. Here then we have to figure out our the extent of those u and v components, and like I had defined, if I swap back over again to my display here, I'm going to use these limits that I did here. So u is going to go from 0 to 2 pi, and v from 0 to 3. So here u goes from 0 to 2 pi, and v goes from 0 to 3. So since none of this depends on u at all, I'll immediately pick up a factor of 2 pi. And then I just have an integral from 0 to 3 of minus 3v minus v cubed dv. And that one is relatively straightforward. I can actually also take the minus sign out here to make those both positive. So minus 2 pi, and then I have 3v over 2, so or v squared, plus v to the 4th over 4, all of that from 0 to 3. And if we evaluate all that, it becomes minus 135 pi over 2. So that is how much of this passes through the surface. Since it's negative, it actually tells you also something maybe about the direction that it is passing through that surface. But yeah, that's how we might evaluate one of these. We first have to figure out what is our dA, and then dot product it with our vector field f, and then we can perform the integral. But finding the dA is usually the hardest part here. Okay, so thanks for sticking with me through all of that. I know it was pretty bad there with the surface integrals there at the end. The nice thing about surface integrals, though, that we will see is most of the time we don't have to do any of the actual integration at all. We will see on Wednesday that we will be able to exploit symmetries of problems in order to perform surface integrals and evaluate them, or find useful ways of using them to find useful quantities like things like the magnitude of the electric field by exploiting symmetries of problems and avoiding the integration part altogether. So I'm going to end it there. Thanks for sticking around. I will see you on Wednesday, and please bring some questions because I know this was a little bit scatterbrained, and I apologize for that, but I will see you on Wednesday.